Hey everyone, and welcome to section 9.6. Today we're talking about graphing quadratic functions using properties of the equations. So basically what we're going to be doing is looking at kind of important features of graphs of quadratic functions, and we're going to look at how those features are manifested in the equation. So to start with, the square function f of x is given by f of x is equal to x squared. We already know this. Jumping off of that, we have that a quadratic function is a polynomial function with degree 2. So it looks like f of x equals ax squared plus bx plus c. Looks familiar. The curve that is formed by the graph of a quadratic function is known as a parabola. So let's take a look at what those look like. Right, so here I am going to graph these two functions, f of x and g of x, and we're just going to do it by plotting points. So here for f of x is equal to x squared, we're just going to pick a number of values, let's say some negative ones, and also 0, 1, and 2. See how that goes. Of course, these are really quick calculations, so all right, if we graph all of those points, and play connect the dots, we get something that looks like that. So that's a parabola, that's the graph of f of x equals x squared. We're going to do the same thing with negative x squared. We'll pick the same x values, so negative 2, negative 1, 0, 1, and 2. But notice we're basically doing the same calculation, except the answer always ends up being negative for g of x, and that's because of the order of operations, right? We square the number first and then multiply it by negative 1. Let's graph all those. And connect the dots. So there we have our two graphs. Okay, now the only difference between f of x and g of x is that sign on g of x. So the sign of the coefficient in front of the x squared term tells you something about the orientation of the parabola. So assuming that a is a positive number, we look at f of x and how the sign plus or minus affects ax squared plus bx plus c, the sign in front of a. And as I said before, it determines the orientation of the product. So we have two cases: if the sign of a is positive and if it's negative. Well, if it's positive, we have the same kind of situation that we saw with x squared, where it opens upwards. And on the flip side, if the sign of a is negative, then the parabola opens downwards. All right, now let's look at some examples of parabolas, see what else we can figure out. We have our general equation, and here are some examples of different kinds of parabolas. So parabola can be wider or skinnier, so to speak, depending on the equation. It can be facing up or down, and it can be shifted away from the origin. So let's look at some important features. Number one, we want to look at the fact that these graphs are all symmetric, right? They all have this line through which the image on one half of the line is the mirror image of the other half. So each parabola has this so-called axis of symmetry. And also of note here is that the axis of symmetry goes through the same part of each of the parabolas. goes through these points at depending on whether the parabola is opening up or down, the crest of the hill or the lowest point in the valley, if you like. So the vertex of a parabola is this either highest point if the parabola is opening downwards, or the lowest point if the parabola is opening upwards. So where do we get those based on the equation for the quadratic function? Well, we get the axis of symmetry from the first two terms. We have a and b, the coefficients of x squared and x respectively. And the axis of symmetry is a vertical line with the equation x equals negative b over 2a. So that's not too hard. And then the vertex is whatever the value of the function is at the x value of the axis of symmetry. And that kind of makes sense because the axis of symmetry goes through the vertex. So here's a picture for reference. So the axis of symmetry is that thing, and the vertex is that. Right, so the axis of symmetry really does go through the vertex, and that's why we use this value, this negative b over 2a, to calculate the y-coordinate of the vertex. Alright, so for f of x equals 2x squared minus 4x minus 3, what we want to do is determine these three things. So to start with, I want to determine the orientation of the parabola. So what we do here is look at the coefficient of the x squared term, the quadratic term, and we see that, oh, it is positive. So that means that the parabola opens upwards. Next, we want to determine the axis of symmetry of the parabola. Well, we know that that's given by the equation x equals negative b over 2a. This is going to be equal to the negative of negative 4 over 2 times a, which is 2 times 2, or 1. So the axis of symmetry is the vertical line x equals 1. And now the vertex of the parabola, we just have to plug in the x value that we got for the axis of symmetry. So we get that the vertex of the parabola is negative 5. So there's another important feature of parabolas that we are already kind of familiar with. It's just a general feature of graphing curves. So I'm talking about the intercepts. We find the x and y intercepts of a parabola exactly the same way that we found them with linear functions. So for an x-intercept, we set the y value equal to 0 and solve for x. And for the y-intercept, we set x equal to 0 and simplify. All right, so remember that it's kind of a tricky thing knowing which variable you're turning into 0, but when you complete the problem for the x-intercept, you should have an x value, and for the y-intercept, you should have a y value. So those are the variables that should be remaining in your equation. And in general, it's possible for a parabola to have actually two x-intercepts. So all this song and dance that we did about solving quadratic equations really boils down to, in some sense, finding x-intercepts of parabolas. And that's just one way to look at it. That's not necessarily the only thing that we were doing. So yeah, there are exactly 3 situations that you can run into when you're looking for the x-intercept. You're solving essentially this equation, ax squared plus bx plus c equals 0, And we already know about these three cases. They depend on what the value of the discriminant is, b squared minus 4ac. So really, these are the situations that you could run into. If you have two real solutions, that means that the graph crosses the x-axis twice. You know, it's possible to have two real solutions to a quadratic. If you have one real solution, that means that the vertex is on the x-axis. And if you don't have any real solutions, then that means that the parabola is on the wrong side of the x-axis, so to speak. So if it's opening upwards, it's above the x-axis, and if it's opening downwards, it is below the x-axis, so it never touches it. All right, so we'll go back to our example. I'm going to determine the y-intercept of the parabola and the x-intercepts, if there are any. So for the y-intercept, I'm just evaluating my function at 0. So that's easy enough. The y-intercept is -3. And the x-intercepts, let's solve that. So we set f of x equal to 0 and solve for x. So we can do this with the quadratic formula if we like. -b, so this would be +4 plus or minus the square root of b squared minus 4 times 2 times -3 all over 2 times 2. Then we just simplify. Alright, we end up with 2 plus or minus the square root of 10 over 2. If you throw that into your calculator real quick, you get approximate values of -0.58114 and 2.5811. Alright, so let's throw all this together and graph. Here we can summarize a little bit. Alright, so let's put all of that information into our picture. So x equals 1 is the axis of symmetry, which means I want to draw a vertical line at x equals 1. Okay, now I know that 1, -5 is my vertex. So that's fine. -3 is the y-intercept. And then the approximate x-intercepts are -0.58114 and 2.5811. So we just do our best, eyeball it. And let's see what we can do. And there we have our graph. Okay, so that's really it for looking at the properties of quadratic functions, what we're going to do next is look at it from kind of a different perspective. And we're going to talk about transformations of the original function instead of just properties of the equation. So, you got that to look forward to.